Well, we're going to get started. Good morning. Welcome back. Hope you all had a good day yesterday and that your morning is starting off just wonderful today. We're going to finish up chapter 3, or at least what we're going to cover in chapter 3 in section 3.2. And then we'll look at some examples of where these scatter plots and regression lines show up and how they are used. And then that'll be it. So we'll go through this stuff here. We'll start back in our presentation from yesterday. Come on, go away. There we go. And that started at that screen. That's not what I wanted to do. Boom. That's where I want to be. All right, so here's where we're starting off today. We're interpreting computer regression output. This was something that was suggested that I absolutely should cover to make sure that you know how to read one of these in case it shows up on the AP exam. So here one is. A number of statistical software packages produce similar regression output. You need to be sure that you can locate the slope, the y-intercept a, right, slope b, y-intercept a, and the values of s and r squared. All right. And in this type of output here, it's the Minitab output. Your constant lines up here with your y-intercept. Right, we have predictor, coefficient, this other thing we're not using, and these two things that aren't being used in this case. All right, the coefficients here, we have our constant, that's your y-intercept, and the miles driven goes along with our slope. The miles driven is from the context of a problem. Right, going back to one of the examples we saw yesterday with the used car, the Ford F-150, and the miles driven versus the price. Right, and this is the slope, 0.16292. Right, so this would be B, this would be A, and the y hat equals A plus BX. So you could write the linear regression equation using these two numbers here. We also have S, the standard deviation of the residuals, and R squared. Notice there's two versions of R squared. We're using the one that's not adjusted. All right, so we have 66.4%. As a decimal, that would be 0.664. Right, so we need to be able to find those values. Those are the ones that we're going to be asked to interpret. What do they mean in context? All that kind of stuff. So being able to read the output and find the appropriate numbers, that's important. Okay. Is there any questions on this computer output before we go to the next type that you'll see? All right. This is another type of computer output. It looks, it's in a different format. Right? Again, we still need to find the slope B, the y-intercept A, and the values of S and R squared. Right? In our summary of fit here, we have R square, we adjusted R square, root mean square error, mean of response, observations, right? R square is R squared. In the other output, it was given as a percentage, and this one it's given as a decimal, 0.664248. This root mean square error, that's our standard deviation of the residuals, right? S. Okay. We have our parameter estimates, right? We have term, intercept, and miles driven. So this is kind of nice. We want the y-intercept, and it's actually labeled as intercept in this printout. That's helpful. All right, so we have our y-intercept here, the value of a, and miles driven. We have our slope. Again, we're not necessarily using these parts over here in this printout. Not for this interpretation. Right, so again, we have all the parts that we might be asked to interpret. They're just giving them to us. So they may ask questions like, what does, r squared or s represent in the context of this problem? What does it mean? That's what we'll be asked to be able to do. Is there any questions about this format of output? All right. So we can also find a regression equation using means. Using technology is often the most convenient way to find the equation of a least squares regression line. It is also possible to calculate the equation of the least squares regression line using only the means and standard deviations of the two variables and their correlation. So if we have R, and we have the mean and standard deviation of both sets of our quantitative data, like of both lists, we can use that to then get the equation of the least squares regression line. And explained here, we have data on an explanatory variable x and response variable y for n individuals. From the data, we can calculate the means and standard deviations of the two variables and their correlation r. The least squares regression line is the line y hat equals a plus bx with slope b equaling correlation r times the standard deviation of y divided by the standard deviation of x. And the y-intercept is a equaling y bar minus b times x bar. So we're using these standard deviations here, kind of like rise over run, y over x. It's kind of how we would use it in a linear equation, right? But we're multiplying it by r to get our slope. And then we're taking into account y bar and x bar when finding our y-intercept. Okay. So we can find this equation mathematically if needed. Okay. I do believe these are in the equation. Okay. See, we need a moment to write any of this down for their notes. So correlation and regression wisdom. Correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, be aware of the limitations. 1, the distinction between explanatory and response variables is important in regression. We have here miles driven versus price, where miles driven is our explanatory variable and price is the response variable. And we have our least squares regression line, S and R squared. For that, if we switch these, where we have price being the explanatory variable and miles driven being the response variable, right? If we graph these incorrectly, we're going to get different results. Notice we have a much more steep regression line, a more negative slope. S is different. It's at 28,716 as opposed to 5,740. R squared stays the same. Right. The least squares regression makes the distances of the data points from the line small only in the y direction. That's why S changes so much. Right. in the scatter plot that we're supposed to use, right? We've reduced this line, kind of reduces the distance between itself and all the points this way. When we change this and we're using these much larger values for miles driven, that's going to change everything a lot because the line's trying to get as close as it can to these other points that are a larger amount away from it. Okay. Now, correlation, which has, it doesn't care if you switch X and Y. Like the value of R will stay the same. We see that with R squared as well. And that has to do with like order of operations and things, but I'm not getting into that. So again, you need to be very careful on how you graph this. If you switch which one's on the x-axis, which one's on the y-axis, even if you have all the correct data and all that stuff, you'll get the wrong regression line, which will mess up if you're trying to make predictions and all that stuff. Got to be careful. Make sure your explanatory is on X, response is on Y. Number 2, correlation and regression lines describe only linear relationships. Right. You can calculate the correlation and least squares regression line for any relationship between two quantitative variables. But the results are useful only if the scatter plot shows a linear pattern. You should always plot your data. See what it looks like. We have these 4 scatter plots here. Which scatter plot do you think has the highest correlation? And we have A, B, C, and D. Take a moment, think about it, and put your guess in the chat. Which one of these has the highest correlations? Which one has the highest R value? Just based on what you know so far. Take a stab at it. All right, we've got a guess for C. You guys take a guess. There is no risk in being wrong here or being right or anything. Just take a guess. All right, we'll try it this way. If you think A will have the largest value for R, raise your hand. Use a little virtual raising of your hand. All right. If you think B will have the largest value of R, raise your hand. All right. If you think C will have the highest correlation, raise your hand. All right, and if you think D will have the highest correlation, raise your hand. All right. Okay, so here's the surprising part. This wants to cooperate with me. Go. They're all the same. Each of these graphs produces the exact same correlation. 0.816. Which is kind of surprising. All right. They also all have the exact same regression line. Y hat equals 3 plus 0.5x. All right. So this is just here to illustrate the importance of graphing your data. We know, or hopefully we maybe remember from yesterday, like graph B is not an appropriate, we shouldn't use a linear model to model that because it's curved, it's obviously curved. Right, and when if we were to plot the residual data, we would get a curve, an obvious pattern from that. Right. Option D, you know, we have that one outlier that makes the whole rest of the thing go crazy. That one point, which is obviously an outlier, causes the pattern to change. Right, so you have to plot your data to see if a linear model is appropriate. Right, the least squares regression line is only appropriate for something that can be modeled with a line, or reasonably modeled with a line. Okay, so you have to be careful. Anything I can clarify about that? Three, correlation and least squares regression lines are not resistant. Right, we already know that the correlation R is not resistant. We talked about that yesterday. And that's partially because R is determined using means and standard deviations, which are also not resistant to outliers. One unusual point in a scatter plot can greatly change the value of R. The least squares regression line is also not resistant. And so we have this graph here where we have child 19 and child 18 that are outliers. 19 is outside the pattern and 18 is way outside the cluster. So they're not typical of what we would expect based on the rest of the data. They would be considered outliers. And so this is the regression line we get, including those data points. If we remove child 18 from the data, the regression line changes. It's going to be a little bit less steep and a bit more accurate to the cluster of data. If we remove child 19, we get a more steep curve or line here. That's, I think, obviously because of child 18 over here. And so removing those is going to have a drastic change, somewhat drastic change on the slope of the line. Right, and we can see with all 19 children, we have R as negative 0.64. Right. Y hat, we have 109.874 minus 1.127. Okay, we have without and without child that, and we can see the changes in our R and our least squares regression line. They will not be the same. Okay. So again, correlation and least squares are not resistant to outliers. Those extreme points will make a difference. Least squares lines make the sum of the squares of the vertical distances to the points as small as possible. A point that is extreme in the x direction with no other points near it pulls the line towards itself. We call such points influential. An outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction but not the x direction of a scatter plot have large residuals. Other outliers may not have large residuals. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. Right. So this is making a differentiation between points that are outliers in the y direction and points that are outliers in the X direction in relation to the overall pattern of the data. They have a slightly different effect. Okay. Is there any questions about that? And would anyone like a moment to write any of this down for their notes? Okay. And so then that actually is the end of the lesson for 3.2 that we started yesterday. Okay. So we learned how to interpret the slope and y-intercept of a least squares regression line, right, what those mean in context. We can use the least squares regression line to predict y for a given x. We can calculate and interpret residuals and their standard deviation, mostly using calculator. Explain the concept of least squares. Determine the equation of a least squares regression line using a variety of methods. Right, we can use our calculator, and if need be, we can use math using the means and standard deviations of y and x of our two variables and the correlation r. We can construct and interpret a residual plot to assess whether a linear model is appropriate. We can assess how well the least squares regression line models the relation between two variables, and we can describe how the slope, y-intercept, standard deviation of the residuals in R squared are influenced by outliers. Right, and that's it. That was annoying. Sorry, guys. Trying to use my document camera, but it decided not to fire up, so that's always fun. So here's an example that we'll look at here. It's gonna make it harder for me to do this because I can't draw on this thing. So let's see if I can make this work. We have a scatter plot here. Right. And this is from a previous year's AP exam. It's a free response question. The manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of the checkout line, data were collected on the number of customers in line who were in front of the selected customer and the line in seconds, until the selected customer was finished with the checkout. The data are shown in the following scatter plot along with the corresponding least squares regression line and computer output. All right, so we have our scatter plot here. Each dot represents the number of customers in line ahead of someone who was randomly selected and how much time it took for them to finish checking out. Right. And there's our least squares regression line. We also have the computer printout here. Right, this is given more in the form of the Minitab one that we saw. Oh, sweet. Okay. All right. And so real quick, let's see if I can make this do what I want it to do. Probably not. Why can't they do no? Really? You don't do me like that? That's annoying. Okay, well, this just keeps getting better. Can't do what I want to do. All right. So we have our constant here that represents our y-intercept. We have our customers in the line, right? This value, 174.4. Okay, yeah. That's essentially seconds of waiting per customer in line. All right, this is our slope. And we have S, R squared, and those are the four values we're most interested in. Identify and interpret in context the estimate of the intercept for the least squares regression line. All right, well, we already saw it here. It's 72.95. Right, and that's our y-intercept. Right. So that's our estimate of the intercept. We also need to interpret it in context. So essentially it means if there are no customers in front of the customer being tracked, it will take about 73 seconds for that customer to be checked out and to be done. Okay, so if they enter an empty line, right, no one in front of them, 73 seconds, a little over a minute, and they're done checking out. Okay. Part B, identify and interpret in context the coefficient of determination, R squared. Well, we have R squared here, 73.33%. And again, remember that R squared allows us to determine essentially how accurate our least squares regression line is and how much of the variation essentially it can account for. We're at 73.3%. All right. And it indicates, get my notes, that 73.33% of the variability in the times it takes customers to finish checkout, including time waiting in line, can be explained by knowing how many customers are in the line in front of the selected customer. Essentially meaning that our model, the linear model here, is good 73.33% of the time. It's a good estimate. And it shows that the customers have a large, the number of customers in front of you plays a large role in how much time it takes. All right, part C. One of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why the point is considered an outlier. So if we go up here, most of our points are pretty close to the line, and then there's this guy. All right, that point where x equals 3, and it's almost at 0. Like, I mean, it's probably maybe at like 73 seconds, kind of similar to the y-intercept. And I mean, we can think of it as it's really far away from our regression line and really far away from the main pattern in both x and y, like both directions. It's pretty far off. Okay. Yeah. It's just way off from what we would expect, right? Waiting, they only had like a 74-second checkout time when there was 3 customers in front of them. That's very abnormal. Not at all what we would expect, given the general pattern of the data. All right. So this problem is essentially making sure that we can say what these different values mean in context. That's it. That's a general idea. And a lot of it is the same as how we would interpret it if we just were given the equation of a line. Right? It's like, what does the y-intercept represent? What does the slope represent? Right? But now we're throwing in the, okay, we have these other things, the r squared, that says like basically how well this line fits, how well it accounts for all of our information. Right? What percent of the time is it gonna be good? Right? And then, you know, finding outliers. You know, we didn't talk, this one didn't ask us to do anything with S here. Right? But S is like the typical variance from each point to the regression line, about 200 seconds. Right? So we have different things we can say based on the context. Is there any questions? Anything I can clarify about this example? Oh, yeah, see him. All right, and this one's all wacky. Why are you down there? All right, and this is. There we go. So this part, this is actually one of the released questions from the first administration of the AP exam this year. This is actually an excerpt from the 2021 AP Stats exam. They won't use this question again in other exams because obviously it's been released, but this gives us an example of the type of thing they're asking this year. All right, now this one starts with box plots. Right. It then will go to, it's gonna make me do that, huh? Yeah, there it is. Scatter plots, several of them. This is all based on the same context. So we're gonna look through this problem. Don't want this. All right, so attendance at games for a certain baseball team is being investigated by the team owner. The following box plots summarize the attendance measured as average number of attendees per game for 47 years of the team's existence. The box plots include the 30 years of games played in the old stadium and 17 years played in the new stadium. Right, and so we have these vertical box plots. Work the same as if we were to knock it over and do it horizontally and stack them. And we have our average attendance in thousands. We have our two box and whisker plots here. Old stadium, new stadium. Right, so we want to compare the distributions of average attendance between the old and new stadiums. Right. So just using the box plots, obviously we're not giving our scatter plots yet. We're just doing box plots. We can see old stadium just based on this, right? We don't have all the data. We can't say a lot about the shape and the distribution, but we can say it's probably symmetric, right? Or fairly symmetric versus the new stadium distribution, which looks slightly skewed, right? We have a large concentration to the, if we have it knocked down horizontally, the left side, so it would be skewed to the right. Right. We also can see the new stadium has more variance, right? It has a larger range versus the old stadium. The IQR is slightly larger for the new stadium compared to the old stadium. Right? Neither of these has outliers plotted, so there's no outliers. And so we have some things we could say. We can just kind of compare them. We're just looking at the shape, center, and spread. How do they compare? That's all on that one. And then we have a scatter plot here that shows the average attendance versus year. And they have differentiated between the old stadium and new stadium in this scatter plot. Right, so a large chunk over here is all old stadium, and it looks like the new stadium started in 2000, and we have the points over here. Compare the trends in average attendance over time between the old and new stadium. So if we just imagine best fit lines going through these, it would be fair to say that both would have a positive association. Right? And it's mostly linear. Right? And so we have a positive linear relationship for both old stadium and new stadium. Right? It is also obvious that the old stadium's rate of increase was much slower than the new stadium. If we imagine the lines going through these, this has a much slower slope than this one. Okay. So we can say that. And we can't really say much about like location of these because it is going by year, and obviously when the old stadium stopped being used, the new stadium began being used, so there's not going to be any like mixture of these points. And there we go. And we have more representations here. So we have graph 1, which is number of games won versus attendance. Zoom out one spot, right? Average attendance, and then number of games won versus attendance, Wait. Now, they're essentially the same. One is not differentiating between the stadiums. One is. So we do have a little bit of mixture of points in here from the two stadiums, right? But they're representing the same set of data. We just have some categorical variables in there for this one. So graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. Right. And again, scatter plots. We're going to talk about the strength, right? The direction, and shape. Essentially, like, is it linear, curved, last thing. And so we have a strong, right? These are all very well clustered here in a very obvious pattern, strong linear relationship that is positive. We have a positive association between number of games won and average attendance. That's it. That's all we have to explain there. Graph 2 shows the same information as graph 1, but also indicates the old and new stadiums. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Explain your reasoning. And overall, no. The slope of the least squares regression line for the number of games won and average attendance for the old and new stadiums is roughly the same. Right? Even if we were to graph them differently, like we would have this through here, this one might be a slightly different, but overall they're about the same. So this means that the rate at which attendance changes as number of games won increases is about the same, regardless of stadium. And so then part D, consider the three variables, number of games won, year, and stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. So we looked at number of games won, year, and the type of stadium. All right. And we're trying to find out which of those, one, not a mixture of them, which one could be a confounding variable. All right, so if we go back to part A, it was easy to see that higher attendance was associated with the new stadium, which suggests that it was possible that the new stadium caused attendance to increase. Part B, right, we noticed a positive correlation between year and attendance, suggesting that it was possible that the year caused attendance to increase. In part C, we noticed a positive correlation between number of games won and attendance, suggesting that it was possible that the number of wins caused attendance to increase. People like to watch a team win. The number of games won could be a confounding variable in the relationship between attendance and the other variables, stadium and year. Right, it's possible that the team winning more games actually caused the attendance to increase, but that games won was associated with the stadium. Right, players performed better with the new facilities. And year, the team developed over time and got better. Right. Also, year and stadium have to be associated, as the new stadium can only be paired with more recent years. Number of wins may be creating a false perception of an association between stadium or year and attendance. So the games won in this case can be considered a confounding variable. Because it's making it so we can't differentiate between the year and the stadium in relationship to attendance. It's kind of like making it impossible to differentiate which one's actually causing a change in attendance. Hence, confounding. Right. So these are the two most recent examples within AP exams that I could find on how scatter plots correlation, the stuff from chapter 3 shows up. Okay. What questions do you have? What can I clarify? All right, so we'll stop sharing the screen there. All right, so that is what we're covering today. I will continue to work on getting all the materials for chapter 12 and for chapter 3 up and running in Canvas. I'm working on our practice problems and stuff like that right now. And by the end of the week, I will have the multiple choice assessment ready for chapter 11 and 3. And that will ultimately be due before the end of the semester. Yeah, and so next week we'll be doing more AP exam prep as far as looking at sample problems, looking at grading rubrics to see what the graders are looking for, how you should be answering questions. Obviously on the free response questions, multiple choice, you answer by selecting a choice. That's self-explanatory. But we'll be focusing more on the free response questions to get ready for that part of the exam. Other than that, that's all I've got for y'all today. I hope you have a great rest of your day, a great rest of your week, an awesome weekend, and I will see you all next week.